So today's problem is going to be the sliding window maximum. You're going to be given an array of integers nums and an integer k, and there's going to be a sliding window of size k that starts at the left edge of the array, and the window slides one position to the right until it reaches the right edge of the array. Return a list that contains the maximum element in the window at each step. So basically we have a window of size k starting from the first element here, and we want the maximum of this window. So as you can see here, our subarray is 3, 1, 2. The maximum here is going to be 3. We append that to our output, and then we move the list once again, 1, 2, 0. The maximum of this is 2, and so on and so forth. And you can see this table here that I've drawn out, and all of these are going to correspond to a specific max, which will be our answer. Now the easiest way to do this is to initialize a subarray of size k, take the maximum of this, move the L and R pointers 1 unit to the right, and then take the maximum of this over and over and over again. This is going to be the brute force method. And the time complexity of doing this is O of n times k, because every element is going to get processed k times. Well, technically not every element, but you know, if you have a look at this 2 here, it gets processed once, twice, 3 times. And then same thing with this 0 here, it gets processed once, twice, thrice, right? So in the worst case, every element is going to be processed k times, right? And we have n elements. So this is going to be our time complexity. But as you can see, there's a lot of wasted calculation here. So for example, when we slide the window this way, these 2 elements are part of the old subarray, right? So if we kept track of the top numbers from the old subarray, like here, our top numbers are 3, followed by 2, and followed by 1. When we slide the window, and 3 gets booted out, we at least know that the max of this is 2, right? And we don't have to recompute that. And we just have to consider that and this one new element. So if we can have a solution that can cache efficiently, then we can get rid of this k computation and just end up with an O of n algorithm. So let's have a think at how we're going to start caching these things. Let's try to have a look at what it might look like. So initially our window is size 0, and then we're going to grow it to a window of size 1, right? And I'm going to keep an array. I'm going to call this tops, right? And tops is going to keep track of our top elements. So at first we encounter 3. That's our current top element right now. And of course we want a window of size k, right? And in this input, k is going to be size 3. Maybe we don't need all this. And then once that's done, we're going to expand our window to 3, 1, right? So our top 2 elements are 3 and 1. And then we're just going to expand one more time until we reach k. And this is going to be our last element of the subarray, and that's going to be 2. And of course, we kind of want this to be in order, right? Because once we slide our window over here, 3 is going to be gone. So this won't be here anymore. And then we want the next element in line to kind of be the maximum of this portion now. And so for that, when we encounter 2, since 2 is greater than 1, we have to move 2 over here. And you might already notice the problem with this approach. This is going to get really expensive. So just now, 2 has to shove 1 aside and swap positions with 1 to get to where it is, right? But what if our input is 4? Then when 4 comes in, 4 has to swap places with 1. 4, 1, and then since 4 is also greater than 3, it also has to swap places with 3, and this is going to be our new tops, right? Or this subarray. And this is basically insertion sorting, which is a very expensive operation, and the time complexity of this is going to be O of k, because tops goes up to size k, right? And so if our k is really large, then this is going to be a really expensive operation. So that's one problem, and putting that aside, this kind of works for a while. Say we've constructed the tops here, despite the insertion sort being expensive, which is O of k. We take the top element here, no problem, and then we append that to our result, right? And then we have to shift the window to here. And when we shift the window, we get rid of 3 from tops, and then we'll add like 0, right? 2, 1, 0. And we're lucky that 0 is small, so it doesn't have to do like really long insertion sorts, right? And from here, we know our tops is 2. We can add that to the list. It's all good. And then we shift the window, and we want to remove 1. So earlier we got lucky that the element that we want to remove also happened to be our largest element, which was at the very front. But now it's not the case. Our largest element is 2, but we want to get rid of 1. And 1 is like somewhere in this array, right? So we have to go on and look for this 1, which is going to incur another O of k operation to search for the number that we want, which is also not ideal. Not to mention that there's a 4 that's going to be a very expensive insertion. I'm going to fix this solution by tackling the problems one at a time. The first problem that I want to tackle is going to be the expensive insertion sort, because right now we are keeping elements in tops that have no chance of being the subarray maximum. Let's have a look at what I mean. So we start at the beginning, we have a subarray of 1 element, and of course this element goes into our tops element, and then we expand our subarray, and this number at index 1 is going to take over this number at index 0, because when the window eventually slides, we want the next number in line to take its place, right? So of course we keep 1 here. And then I extend the window one more time. And then we have the number 2. Let's have a think about this. For now, let's not consider what any of these actual numbers are. I just want us to have a look at the numbers from our original array. Now, the next maximum is 2, right? It's not 1 because 2 is larger. And if I move it again, now 1's not even in our window, we have these elements. So from here, the number that can influence this current window from the original first subarray is the number 2. So if you think about it, the number 1 is useless. Number 2 here is both younger and larger than the number 1 here. So no matter what happens, this number 1 can never succeed the number 3. I kind of think about it as like the person with the largest dong. Like without surgery, you can't really change the size of your member, right? So if you have a guy who's like the reigning champion, right? He's like, I don't know, man, like 20 inches or something, right? And then you're born, yours is pretty big. It's like a 12, right? That's pretty impressive. But like you're not him, right? You're not him. But because you're younger, you can kind of wait for him to die, and when he dies, you become the biggest guy, you know? But if then somebody even younger than you is born and he's got like, I don't know, like a 16-inch pecker, when this guy dies, you will never be number 1 because he's gonna be number 1. He's the next number 1, right? And there's no world where you can dethrone him because not only is your number smaller, you're also older than him. So you're gonna die first. So you can't do the strat of like wait till the biggest guy dies before you take his place because you're dying first. And that's basically the same situation that we have here, right? Okay, enough dicks. I'm gonna delete this. It's literally the same thing here, right? It's literally the same thing. This guy's younger and he's larger. So 1 here, 1 will never be the biggest. So that's why when we add a new number into our array, in this case 2 here, we will do a while loop and we will check whether they're smaller or not. And if they're smaller, then they're not worth considering. This one is not worth considering. That's why we can just pop it and put the number 2. And these are going to be our tops. And this keeps our tops array lean and only with the elements that have the potential of being the next biggest. All right, let's keep going then. So I'm going to move again, right? 3 gets kicked out of the array. We add a 0. And since 2 is larger than 0, it means that 2 still has a chance of being the top. Well, in this case, it's literally the frontmost element, so it is the top. But regardless, we can put 0 here, and that's going to be our next in line, right? When 2 gets evicted, there's a chance that 0 is the next best thing. So we do it again. And also you notice that when we're going to move this window next, we don't even have to remove 1 anymore because 1's not even here because it was never up for consideration. And that's going to help our time complexity a little bit. This is going to be our next window. We've removed 1. And we want to add 4. And remember, 4 is not only bigger, it's also younger. So 2 and 0 are not even for consideration because they're both older and smaller, right? The only way that it would stay is that if this was a 5 or something, then we wouldn't kick out 5. We would only kick out 0, right? But such is not the case right now. So both of these are going to get popped. 4 is going to get added to our tops. I forgot to keep track of the maximums that we had so far. It should be 3, 2, and now 4. We move this again. We add a 2 here. 2 is going to take the place of 4 if 4 gets evicted. So we add that in. And then for this subarray, it's 4. One more time. We shrink this, get rid of 0. 0 doesn't even exist here anymore. We find a 6. Evict these 2, add 6 in, and that's going to be our next top. Our top is always going to be the first element, and that's going to be our result. It works pretty well. Now, the other problem that I kind of glazed over was the problem of shrinking. I said that we need a full scan for this to work, but that's not really the case. So with this structure, we know that the first element is always going to be the oldest element. And this is a lot more clear if I use the indices instead of the value, right? So the values are unchanged. When we slide here, we want to remove index 0, right? That's going to give us this subarray. And then when I move here, I want to remove index 1. And when I come here, I want to remove our index 2, right? And so on and so forth. So this starts with the oldest element and then asks for like a younger and younger number by 1 each time, right? And what do you notice about the indices at tops? Let's run through this real quick. We remove index 0 here, so this is gone. We're left with a 2. And then we want to add a new element at index 3, right? So our vals is going to be 2 and 0. And then the next step, we want to remove a 1. We don't have a 1 here, so we still keep our indices, but then we add a 4, which pops all of this. And what you notice is that our indices here are always going to be in ascending order. The smallest index that we have will always be at the very front. When we shrink arrays, we're looking to remove the oldest element, the smallest index one at a time, right? And the smallest index has to be in the very front. And if it's not at the very front, for example, in this case, when we try to remove a 1, well, it just means that it's already been kicked out. And the front is going to be a younger element that the window shrinkage just hasn't really gotten to yet, but it'll come. Oh, and one small note. For this example, I changed our tops to use indices instead of of the values. And I'm going to keep this change when we move to the coding section, because when we shrink our arrays, we're actually trying to remove an index instead of the value. I just kind of used values in the beginning because it's easier to understand. And you know, I think we're ready to code. So first things first, we need a result array, and this is going to store our output. And the next very essential to this algorithm is our tops list. And if you notice here, I'm not using a list, I'm using a deck, a double-ended queue. And this is because when we shrink our array, I want to be able to pop left to cut the head of the list, right? And pop left is not an operation available in regular lists, which is why we're using a deck. Next, we'll have our L and R pointers. And then I'm going to put a little sample here, just so we can follow along with the code as we go along. At first, this is just going to be our initial input with nothing going on. So first of all, our window doesn't even exist yet. We want to initialize our window and make it grow to this point, right? So let's write a for loop for r in range k, because k is the size of our window. I want to append r to tops. But of course, it's not just going to be a simple append. We want to pop the elements that came before it if it is smaller, right? So this is going to be our first insert. We're going to get a 3, then a 3, 1. But when we insert a 2, 2 has to continuously check for the previous value here and pop it if it's smaller. So while tops has an element, of course you can't do this check if it's empty, and this number that we're trying to insert is greater than, well, tops minus 1 is going to give us this thing, and then we plug it into nums, which will give us the number 1, right? So while this number that we're trying to insert is greater than 1, then I need to pop. And after we do this loop k times, we would have successfully constructed our initial window, and we can simply append the number in the very front of our deck. So there you go. And now here comes the growing and shrinking part. We continue with a while loop because r here has to go all the way to the very end. Now we have to write our shrinking logic. So in the next iteration, we can expect the front of the subarray to be popped if it hasn't been done so already. So if tops 0, this is the index, is equal to L, which is what we're trying to shrink, then we need a pop left. And that executes in our current case. It's going to pop 0 from here because 0 is the same as L right now. And then we increment L by 1. And then that's pretty much the shrinking logic. And then the growing logic here is pretty much the same thing. We increment R by 1. So from here we go to here, and it's pretty much the same thing with while tops, and the number they're trying to is greater than the last number that got added to tops. Then we want to keep popping, and once we're happy, we append R to tops. So after the shrink and the grow, we have our next proper window, and all we have to do is just append the frontmost number to our result. And if we follow through the algorithm, we should have 3, 2, 4, 4, 6. And that's our code. Oh, I kind of messed up. This should be in the while loop, and then we need to return result here. And there we go. That's going to be the solution. As for the time and space complexity, each element is going to be added to tops once, and it's going to get removed once. So the time complexity is going to be O of 2n, which just simplifies to O of n. And as for the space complexity, we have result and then we have tops, right? We know that the result is basically size of O(n) minus k, right? Because there's n minus k subarrays, and our tops, as we know, is O of k. So the total space complexity is the sum of both of this, so I'll say O of n. And that's about it. Thanks for watching.